Okay, so here we go. 4.1 is remarkably short. A lot of it's review. Just make sure that you remember how Taylor polynomials work. Formula that you should recognize, fundamental properties that you should recognize. This is all Calc 2, right? So the big idea, of course, is that it's just a polynomial that mimics the function by having the same value, the same derivative, the same second derivative, etc., up to a certain point depending on the degree of the polynomial. So for multivariable functions, we just do the same thing. It's morally equivalent. We're looking for a polynomial that mimics the function by having the same value at a given base point, the same, it's tempting to say derivative, but of course there's a bunch of first derivatives, namely all the different partial derivatives. So all of the partial derivatives need to be the same. And then likewise for the higher partials, so all of the mixed higher partials likewise, up to again a certain point depending on the degree of the polynomial that we're talking about. So the formula for how to do this is just a formula. Here it is. This is I'm only going to show you the degree 2 Taylor polynomial, because this is all we'll be making any reference to. The formula does get a little bit weirder the higher up you go. So notice it looks a lot like the single variable Taylor polynomial, f of a. Boom, rip off, right? Now, this is where we would normally put f prime times x minus a. Well, now we have a derivative matrix times the vector x minus a. So it's no longer a scalar product. Now it's a matrix vector product, but it's still the derivative times the displacement. It's really morally equivalent. Here's the second order term. A little bit weirder, but notice this thing here, called the Hessian matrix, is made up of all the second partials. This Hessian matrix, organized as indicated here, kind of plays the role of the second derivative. And notice how this term, likewise, looks a lot like the single variable version of the formula. So this is going to be our main object of interest, frankly, is the Hessian matrix. It turns out that this is going to be a key part of the second derivative test that we'll get to. And thus ends our discussion of section 4.1. I told you it'd be quick. Not that much to it. Okay. On to 4.2. Extrema of functions. Again, a bunch of review. Here's a bunch of single variable calculus stuff that I think y'all remember. And that is that if you're looking at a point, kind of like, let's say this point here or this point here in the domain of some function, we're looking here at the graph of some function. If these three properties are satisfied, then the function is in the process of increasing. There is therefore no way that this could possibly be a maximizer that we're looking for, like if you're trying to find the maximum value of f. It's definitely not happening here. Because look, you're in the middle, you can go either way you want, left or right, and the derivative's non-zero, so that means, for example, in this case, as we go to the right, at that point the function is in the process of increasing. You can't be at the maximum if the function's still getting bigger, right? So we can eliminate that point on the basis of this argument. Now, here's the thing, good news. This is satisfied by almost every point in the domain. Right? This argument fails only at very specific points. Namely, it fails at points where one of these conditions fails. So, if the point that you're looking at is not in the interior, and thus you kind of can't, you're up against the edge and you got nowhere to go over there, right? Or if the function's not differentiable and therefore you can't make a reference to what the derivative tells you, there is no derivative. Or if the derivative is zero, and therefore not really telling you anything about the function increasing, because, well, zero is just kind of, nothing happens when the derivative is zero. So if either one of these conditions happens, in other words, if any of the green conditions fails, then what do? We have no elimination argument. We basically don't know what to do. So we don't claim that it's definitely a maximum, because it's not necessarily. right? But we do throw up our hands and say, I don't know what's going on with these points. So we call them critical points, and we promise to take a closer look later. It's basically what we do there. So let's identify in this picture where the critical points are. Well, boundary points, points where the derivative is 0, points where it fails to be differentiable. Other than these points, the elimination argument eliminates everything else. So all of these values, all of these values, all of these values, and all of those values, we know for sure are not the maximum that we're looking for. And only these red critical points remain. Okay, so again, that's all review. That's single variable calculus. Here's the multivariable version of it. It's morally equivalent. Here's the big idea. Most of the time, these conditions are going to be satisfied. Let me document what they are, and I'm going to think in reference to this point right here. It's in the interior of my two-dimensional domain. The function is differentiable there. You can't really tell that from the picture, but I'm going to say we're going to suppose that the function is differentiable at that point I've selected. And the gradient's non-zero as suggested by the fact that, I'm trying to draw the graph being kind of uphill, at that point. So the gradient is something like based on how I have the picture drawn, maybe something kind of like that. Right. So, could this possibly be a maximizer? No. Just go in the direction of the gradient. We know we can go that direction because we're in the interior. We know that as we go in the direction of the gradient, the function's increasing. And if the function's increasing, can't possibly be a maximizer. Right? So again, we have a tool here that's going to eliminate most of the points in the domain. The precious few exceptions, the ones that we can't eliminate. Oh, I should do this in the pen mode. The ones that we can't eliminate are the ones on the boundary, right? Or the ones where the function fails to be differentiable. I just need a little bit more room here, so I'm going to zoom out. Point like this, where the function fails to be differentiable, right? Or a point where the gradient is not non-zero, aka where the gradient is 0. So that would be here, and here, and here. Everywhere else, which let's see if I can just shade in everything else in green. Everything else is eliminated by this argument. So the analogy with single variable optimization is overwhelming, right? It's the same deal. Take the gradient, set it equal to 0. Don't forget to look at points where the function fails to be differentiable, and don't forget to check the boundary. Now, asterisk, how to check the boundary, we're going to get to that in a few minutes. There's some sticky issues there. But same ideas, basically. Okay. All right. So, just for fun, I'm going to point out that points where the gradient is 0 could be maxes, like we see here, right? But there's more dimensions to move around when you have two independent variables, and there's different kinds of critical points that look different. For example, there's the idea of a saddle here, right? If you imagine this would be like a mountain pass, if you will, back to hiking metaphors. So there's various more of these kinds of things as well. It gets weird, and I think a fun thing to Google just to kind of see what the other possibilities are. Do a Google image search on the term monkey saddle, and what you'll see is some kind of weird surfaces that they're very different. I mean, something like that just can't be done in single variable graphs. Right? And then you will also see, if you scroll further down, that somebody actually put a monkey in a little saddle on a dog. It's kind of funny. Anyway, I don't know if you're into that sort of thing. Okay, so here's an example. We've got a function here we're going to find all the critical points. Recall that there are 3 things to check. We need to check points that are on the boundary. Let me go back to the list. Got to find points that are on the boundary, points where the function fails to be differentiable, and then I got to take the gradient and set it equal to 0. So, nothing to it. Let's see here. This function's defined everywhere. The domain is the entirety of R2, which has no boundary. Therefore, every point's in the interior. Therefore, we don't have any boundary critical points because there is no boundary. All right, so that was easy. This is a polynomial. Polynomials are differentiable everywhere. So there's no differentiability failures either. Right? All right. Now notice how easy it was to check these first 2. It's just mostly a matter of kind of writing it down and observing, yeah, there's no problem. Right? So easy to do. Now I have good news. It's going to sound like bad news. It's actually good news. The good news is you do have to put this down. These are worth points. How many points is at the discretion of the grader? No promises on that. But so the good news is, for very little effort, you get points. That's good news, right? Now, the glass half empty take is, oh man, I'm going to get points counted off if I don't do this, right? Well, again, that's very glass half empty. Just do it. It's easy, right? And again, free points. I thought I saw it. Yes.
Yeah. So if this is bounded, for example, if you have a domain for x and a domain for y that's bounded, wouldn't that be a curve?
Yep. We're going to get to boundaries in a few minutes. Yep, absolutely. All right, so let's get to the rest of this example. So we've checked conditions 1 and 2. Now let's take the gradient. No problem. We set the gradient equal to 0. This results in a vector equation, which is easy to solve because when a vector is equal to another vector, what that means is that the corresponding coordinates are equal, just pairwise, right? So what I have here is just 2 scalar equations, right? And conveniently in this case, the first one tells me what x might be. There's 2 possible values of x. And the second one tells me exactly what y has to be. There's only one possible value of y. And all of this together gives me my 2 critical points. So the algebra on this one works out really nicely. Everybody on board? It's very straightforward stuff, right? Okay. All right. Now, to be fair, sometimes the algebra gets weird. And let's suppose, now let's not worry about the optimization problem this may or may not have come from. That's not my point. I want to point at a vector equation here, where the solution to the vector equation can be, there's a landmine that a lot of students step on, and it's very worth noting what the landmine is and how to avoid accidentally stepping on it. And that is, don't make the mistake of just assuming that when you have x squared equals y squared, for example, that means that x is equal to y. Right? Now, in a lot of high schools, mine included, there were courses where, don't worry about it. Right? They just swept this under the rug like that's okay. It's absolutely not okay, right? If x squared is equal to y squared, there are 2 possibilities. X could be y. That's possible, yeah, but it's also possible that x is negative y. There is nothing about this that is somehow, subservient to this as a possibility. They're equally valid ways to satisfy the given equation. So if you're looking for the set of all solutions, you have to consider all of the cases, and that means you got to break it down into case 1, where x is equal to y, and then a whole separate consideration, case 2, where x is equal to negative y. Right? So let's take these one at a time. Let's suppose that x is equal to y. We're looking at case 1. Well, if x is equal to y, what happens to this equation right here Well, you plug in x equal to y into there, and what we have is that becomes this. Right? And that's easily solved. And if you know that x is equal to y, that gives you these values of x and therefore these critical points. Okay, so case 1, no big deal, a little bit of algebra plugging in, but again, don't forget to do case 2, right? Case 2, x equals negative y, you plug that in, notice that this equation becomes different. It's not the same as what we had before. So we have different algebra to solve to find the appropriate values of y. And then, with these different values of y, notice that with x equaling negative y, in this case, we get more critical points. Now, one of them is a duplicate, right? So altogether, let's see here. Altogether, there was a critical point. There was a critical point. This one we already had. It's not real. It's not a critical point twice, right? We just found it twice. But then we certainly did get a third critical point. And if you're casual about the cases and a little too sloppy with your algebra, then you will miss critical points like that, which is significant. Does everybody see the problem in the resolution? Okay. Second derivative test. We've already made the observation that the single variable second degree Taylor polynomial, right, and the multivariable second degree Taylor polynomial, highly analogous. And in the same way that the second derivative makes up the second derivative test, thus the name, right, in single variable, well, likewise, the second derivatives, this time in the form of the Hessian matrix, are basically the point, to the second derivative test if you're trying to classify critical points. So, all right, now what do we need? Well, I need to know when this term, which you'll notice is a quadratic form, flashbacks to Math 218, right? This quadratic form, I need to know when this is always positive, perhaps, or always negative, perhaps, or possibly neither, right? And so we've got to be able to identify positive definiteness. And just to add to the complications, well, it's another sort of good news, not bad news. This is a special matrix. This is made up of second partials. And we have rules about mixed second partials, and under certain conditions that are usually satisfied, mixed second partials don't depend on the order. And what that ends up doing is it ends up making this a symmetric matrix. So it's not just that we need to know about positive definite and negative definite. We need to know about positive and negative definite of a symmetric matrix. And there's cool stuff about symmetric matrices. And if you're looking for a linear algebra challenge, this is perfectly doable with Math 218 techniques. But it's a little bit, this is challenging. Right? But if you're looking for that kind of a challenge, these are some checkpoints that you can kind of think through as you reason it through. But you don't have to. Here's what you need to know about the second derivative test is this little flow chart of possibilities. This is all you need to make sure that you know to execute the second derivative test. And it breaks down as follows. If your Hessian determinant is positive, then the second derivative test is kind of exactly what you would think. Look at that top left second derivative. Positive means min, negative means max. Just like in single variable. So positive Hessian determinant means business as usual, kinda. Right? Okay. Negative Hessian determinant means that you have what's called a saddle point. And again, we talked about that, the different kinds of, like you can have like what I like to call Pringles. I think Pringles is the more modern, relevant, right, metaphor than saddles. Very few people ride horses these days. So you have a Pringle point if the Hessian determinant's negative. And what kind of Pringle? Oh my gosh, no comment. right? All sorts of possibilities. We're not going to pick on that. We're not going to go down that road. And then also, there is a third possibility, and that is that the Hessian determinant's 0, in which case the test fails. And likewise, furthermore, notice if the fxx in the positive Hessian determinant case, if fxx was equal to 0, again, the test fails. Right? So the second derivative test does not resolve all questions. It resolves many questions, possibly even most. Right? But it does have these cases in which it just flat fails. Okay. So all this is here is a matter of plugging in. So if we look at this function and we look at these critical points, let's classify them. Right? We'll start with this point here, -1, 0. Classify it. All right. Well, here's our function. Here's our Hessian matrix. There's the Hessian determinant. That's just a little bit of algebra, taking partials, taking a determinant. And you plug in this point to that Hessian determinant. You get negative. That means a saddle. It's just straight up plugging in. Is everybody on board? All right, in the interest of time, I'm going to let y'all read the second half. It's just, again, just straight up plugging in to this little flow chart of possibilities. Okay. The next 2 pages, we're going to skip. This is all supplemental. It's all supplemental. You don't need to know this, right? Now, I like to put it in here because I think it's a nice, while we're on the topic of optimization, I like to include some neat comments about how things change if you're looking for a global maximum, not a local maximum. And anyway, it's not anything that we need to worry about, so we're just going to skip these 2 pages. Making good time. On to section 4.3, and there is a wonderful method here to address a very complicated question that you were asking me about. How do we handle the boundary, right? When we have more than 2 points on the boundary, you can't just check them. There's too many. There's infinitely many points on the boundary. All right, so specifically, we're going to entertain the question where we want to find the max or min value of some function subject to a constraint. Let me show you what I mean by that as an example. Okay, so I want to find a point that's closest to the origin. Now this is an optimization problem. Closest means I want to minimize something. Right? I want to minimize the distance. So that's the function we want to optimize. By the way, optimize, of course, means sometimes you want to minimize, sometimes you want to maximize. We lump them all together with optimize. There's the function we want to optimize. Here's the constraint. I'm not looking at all points. I want to look just at points on this curve, just at points that satisfy this equation. So this is what we call a constrained optimization problem. Okay. And if you think about it, boundaries are constraints because you're constrained to being on that boundary curve. All right. Now we're going to phrase all of our constrained optimization problems as follows. That there is some function, in this case, distance to the origin. Oh, whoops, wrong color. Distance to the origin is what you want to optimize. Now you'll notice I pulled a fast one here. This isn't distance, this is distance squared. Here's the little fast one I just pulled. This is a micro point, but it's convenient. If you think about it, the point that minimizes distance also minimizes distance squared. Right? So anyway, this is convenient to work with distance squared because it didn't have square roots in it. So it's a nice little hack, little mathematical life hack, and that's what I'm doing here. The point, though, what I'm actually interested in is minimizing distance. So we're going to call distance distance squared, the objective function. And then we're going to talk about the constraint as being a level set, and this is very important. It's got to be a level set, right? View your constraint as being a level set. level set of what we're going to call the constraint function. So this is the function up there whose level set defines my constraint. That, therefore, is what we call the constraint function. Everybody with me? We're going to phrase all of our constrained optimization problems this way. We need to have an objective function to be maxed or minned, and a constraint function for which one of the level sets is our constraint. Okay. So just as some examples, here's a question. Suppose you want to find the box of greatest volume that has a certain amount of area. And there's all sorts of boxes, long and skinny, tall and narrow, medium in all directions, various different shapes of rectangular boxes. Well, among those that have a given fixed area, which one has the biggest volume? Right? So, okay, well, the thing that we're trying to optimize is volume. Our constraint function is area. Yes.
Is that surface area?
Yeah, surface area. Yeah, right. Yep. So, constrained optimization problem. Okay. Likewise, suppose we're starting a business and we have a limited budget to be allocated toward various things, and we want to maximize our productivity, whatever that is. Right? Okay, well, productivity is the thing that we want to maximize, optimize, so that's our objective function. And the constraint is the budget. I only have so many dollars that I can spend on labor or tools or materials, right? And however, I can't just go out and spend $1 trillion. I just don't have that kind of money in the budget. So there is a constraint. I have X amount of dollars, and that's all of my expenses have to add up to that. Yes.
So in that case, would the constraint function just be a constant?
Yeah. Well, that is a requirement, actually, right? So to be called the constraint function, we need the constraint to be a level set of the constraint function. Yeah, and of course, level set means it equals a constant. Yep. Does that make sense?
Yeah.
Yeah. Okay. All right. So how do we do this? Again, shockingly similar, as it turns out, to single variable calculus. So we have an elimination tool. And this is it. If everything in sight is differentiable, and if, let's see here, let me do it like this. Yeah, if everything in sight is differentiable, if the gradient of our constraint function is non-zero, I do need my constraint gradient to point in a well-defined direction. We're going to see why. But if my objective function has a gradient that points off of that axis, right? If you think about it, the constraint gradient always points perpendicular to the constraint set, right? Gradients always point perpendicular to level sets. This is why it's key. This is why it's essential that the constraint function be that whose level set is your constraint. It's got to be a level set. Constraint gradient is always perpendicular to the surface. My objective gradient, if you think about it, if it's pointing off that axis, then we couldn't possibly be at a maximum, because look, I can just kind of move along still within my constraint set. I can move kind of in the direction of what you might call the shadow, right? I mean, project that objective gradient, down to the surface. Just go as best you can in the direction of the objective gradient. The function's increasing. Because the rate of change of the function is that dot product per the assumptions, per the picture, is clearly positive. Function's increasing. You couldn't possibly be at a max. Make sense to everybody? Okay. So, again, we eliminate most of the points in our domain this way. The things that we can't eliminate are what we call critical points. And the critical points are where any of the above conditions fail. So you're going to be looking for where either for one of the two defining functions is not differentiable, right? So check them. Again, eyeball glance. It's at a glance usually pretty clear if your function's differentiable or not, right? Just if there's anything weird where you're, dividing by square root of x squared plus y squared, something bad like that, right? Then yeah, sure. But if it's a polynomial, if it's an exponential, things like that, everything's differentiable. Give it a quick look. Easy to check. We got to check for where the constraint gradient is 0. And we've got to check for where the objective gradient is not off axis. In other words, where it's a multiple of the objective gradient. So these are our methods. So here we go. Let's do this optimization problem right here. We want to find the highest. Let's see here. Let me color code this. We want to find the highest point, aka want to optimize this function whose value is just z. Right? The highest point on this surface, and notice that this surface is a level set. Conveniently, it was written as a level set. If it's not written as a level set, rewrite it as a level set. And the function whose level set you're looking at is your constraint function. So finding the highest point on this surface boils down to this constrained optimization problem. And now let's start checking conditions. Let's see, where does either one of these fail to be differentiable? We'll know where they're polynomials. Boom. I just earned a point. Probably. Depends on the grader, right? But look how easy that was. I only had to write down, 10 characters, right? Easiest point you'll ever earn, right? So again, let's take a glass half full point of view on this. This is an easy way to earn points. Don't think of this as, oh gosh, they're going to dock me for not doing it, right? It's easy to do. So just do it. Okay, so differentiability. Now, second one. Where is the constraint gradient equal to 0? Sometimes there is a little bit of work to be done here. It's not that bad. It depends, but usually not that bad. Frankly, what I'm about to show you is one of the harder ones that I've seen. Here's my constraint gradient. How do I know when this is equal to 0? Well, that's a little system of equations. It's 3 equations with 3 unknowns. If I want to know when this, then I'm going to rewrite in matrix form. If I want to know when that is equal to 0, this is a little Math 218 linear algebra problem. Everybody with me? And conveniently, this matrix here is non-singular, and because it's non-singular, the only solution is the trivial solution. Does that ring some linear algebra bells? And so now wait a second. It's tempting to call this therefore a critical point, but do keep in mind when we are looking for critical points, we are looking for points that are actually on our domain, right? I don't care about points that they're not even on the surface. It's got to be on the surface, else I don't care about it. And notice that point that we just found does not satisfy our constraint. It's not on our surface. I don't need to eliminate it. It wasn't a candidate in the first place. So no critical points come about then from this argument either. How we doing? Everybody happy? Okay. Alrighty. So, just a quick terminological thing. For reasons that I don't have time to explain, this condition is routinely called the degeneracy condition. There's a really good reason. We don't have time. It's actually beyond the level of this course as well, but anyway. Just if you hear me say the degeneracy condition, this is what I'm talking about. Okay. And also from a terminological point of view, this one here is typically called the Lagrange condition because this method as a whole is called the method of Lagrange multipliers, and this is the multiplier, they call it. So we call this the Lagrange condition. All right, so we've checked these two, and now on to the third. We need to see where is the gradient of f a multiple of the gradient of g. Okay, well, the gradient of f is that. The gradient of g is that. So I've got 3 equations here to solve. This is your Lagrange condition. Do keep in mind the purpose of the Lagrange condition, again, is to help us find points that we can't eliminate. We don't care about eliminating points that we don't need to eliminate, namely points that already don't satisfy the given original constraint. So really what we're looking for is points that satisfy all four of these conditions. And so don't forget that constraint condition. That's an easy one to accidentally forget, right? So this gives us actually four equations with four unknowns. And now begins the algebra of how to solve. They're all different. I'm going to show you how to do a few of them, right? And in this case, there's a nice little foot in the door, and that is that looking at this equation right here, you notice that we have a product that's non-zero. That means that neither one of these factors can be zero, and more to the point, lambda cannot be zero. Now, knowing that lambda cannot be zero allows me to cancel that lambda from the first two equations, which makes the first two equations then turn into that, which is easy to find some relationships with. This is just how this particular one happens to work out. Again, every example is different. Yes, we conclude lambda's not zero, cancel it, do a little bit of algebra, and then I'm going to take these equations and pop them into the constraint, and out comes z, the two possible values of z. Once you know z, that tells you your x and y, aka that tells you the rest of your coordinates of your point. Is everybody with me? Okay, so the algebra can get a little weird. Let's look at the next one. Optimization problem, objective function, constraint function, blah, blah. A bunch of that's repetition. Let me just show you how the algebra on this one works out. It's a little bit different. Here, there's a strong temptation to solve for lambda in both of these equations. Wouldn't it be nice if we could solve for lambda? Very common mistake students will make is to just, cross-multiply, whip terms around all over the place. Keep in mind, cross-multiplying is dividing, and you're not allowed to divide by zero. So easy little oops to forget to do. If you want to divide by this 2x and take it to the denominator of that term, you first have to establish that it's not zero. Right? So again, easy little mistake to make. Good news, it's just a matter of plugging in. If you can just look at these equations, plug in x equals 0, plug in y equals 0, they don't work. There's nothing to it, right? But you do have to go to the trouble of first establishing that they're not zero. Once you know they're not zero, then solve for lambda in those equations, and that tells you a relationship between x and y. And as usual, once you have a relationship between x and y, you can plug that into your constraint. Oh, missed. Let's try that again. And then a little bit of algebra, and it's all unravels. Okay. Last example. A little bit of algebra here. Again, a lot of the preliminaries, all the same. What do we do with this? Now, very easy mistake to make. A lot of students will look at this and say, okay, well, lambda has to equal to 1. But lambda also has to equal to 1/4. And, while we're at it, it also has to equal to 1/9. Lambda cannot equal to all three of these different numbers. And a lot of students would throw up their hands and say, well, there's no critical points because that's a contradiction. Not true. Because this does not mean lambda is equal to 1. This means either lambda is 1 or maybe x is just 0. If x is 0, lambda could be whatever. So we really, very literally, cannot assume that lambda has to be 1. Right? So what we've got to do is actually deal with this by breaking it down into cases. There are 3 different cases. First entertain what happens when x is non-zero, then y is non-zero, then z is non-zero. I guess technically we have a fourth constraint, or a fourth case. The fourth case would be all three of x, y, and z are all zero, but of course that fails this equation. So we don't need to really bother with that. So what's interesting though, notice if you assume x is non-zero, then yes indeed, you can solve for that lambda. Lambda is 1. When you take that 1 and you plug it into here and here, that does tell you information. If lambda's 1, y and z have to be 0. And that gives you, oh well, not quite. Those you can plug into this equation. That'll let you solve for x. And now, lo and behold, check it out, we've got a critical point. Correction, 2 critical points. Right? So that's just in the first case. And then, of course, there's 2 more cases, each of which gives you 2 more critical points. So if you play too fast and loose with zeros and algebra of, dividing by zeros, you're going to miss a lot of critical points. So please be careful with that. We're done. We made it. Y'all have a good rest of your Monday. Midterm, of course, on Wednesday. Final exam a few days after that. Good luck with your studying. I'll see you later.